Beaver's pilot sees the muzzle flash first. Tracers walk up the sea. The Raptor swings wide behind a gas platform, gyro humming, KPVT spitting 14.5 millimeters. Impacts thump through the drone's shell, but systems stay green. Why? Because the vital organs live in the corners, and the nose is all explosive mass. The pilot yanks vertical, forcing the gyro to chase a target it never trained for, an aerial profile above its own wake. The boat commits to a turn it can't complete. The question is simple. Does the drone escape, and what flaw did the Russians miss? Before we move on, please take a moment to subscribe to the channel and like the video. How does a plywood-bodied drone take over 600 hits from a 14.5 and keep flying toward a protected airfield? It starts with where the ambush waits. A Raptor-Class Patrol Boat tucks in behind a derelict gas platform, using its steel lattice like a blind. The crew holds fire until the last seconds. The Beaver is wave-skimming, riding a thin cushion of air over choppy water. At that height, any warning is late. The boat edges out, bow angled for a short intercept. The remote weapon station is live. The gunner sits below deck, staring at a stabilized sight that cancels most of the hull's motion. The moment the crosshair crosses the drone's nose, the KPVT starts its long burst. Rounds stitch the surface, then rise into the drone. You hear the slap of impacts. The upper V-chord mount stays on target, compensating for roll and pitch. By every rule of thumb, the UAV should be breaking apart. But the telemetry doesn't drop. Speed holds. Heading holds. The payload section stays intact because the layout is hollow by design. The electronics ride in the corners, in small pods away from the center line. The guidance runs along a separated power bus that doesn't share a single failure point. Up front sits the mass the gunner expects to detonate. Instead, it acts like a dense cushion. Pass-through hits vent energy. No fuse path gets completed. The explosive remains inert because nothing critical gets struck the way the gun assumes. This isn't guesswork. Armor-piercing incendiary rounds at 14.5 caliber will punch through thin composites and wood. They overpenetrate unless they meet a dense component or reactive path. UAVs built with dispersed systems show this kind of stubbornness. Loitering munitions designed with spaced wiring and isolated control boards have flown with ragged holes in their skins because the projectile failed to hit the one line that kills the brain. The Beaver borrows that logic. Spread the organs, and the body can take ugly wounds. The gun crew has another problem. Wave-skimming compresses their timeline. At sea level, the target crosses the bow in seconds. Lead changes fast because apparent speed spikes at close range. The wake throws spray into the sight. The platform's beams reflect and create jitter in the tracker. Each correction the gunner makes has to account for the boat's own motion and the water's texture. Small errors grow when the target is only meters above the surface. The Raptor brings real strengths to the fight. It has speed to close and a stabilized mount that shoots smooth strings. The rate of fire is brutal. But those advantages fade at steep angles and during tight maneuvers in chop. At higher speeds, the boat needs a wide arc to turn. The hull leans and couples roll into yaw just as the gun needs a clean line. The stabilizer can keep the reticle mostly steady, but not when elevation and azimuth both change hard while the deck heaves. Now watch what the pilot does with that. The boat commits to a wide, high-speed turn to get a better firing line. The gyro hunts. It chases a target that keeps slipping between sea clutter and mast lines. The Beaver stays low just long enough to make the crew believe it will keep skimming. Then the move comes. A sharp pitch-up. Climb begins from close range, changing the target from a flat, low silhouette into a steep, rising profile that forces elevation rates the mount rarely sees. The ambush fails because the firing solution assumes a fragile center mass. The Beaver refuses that assumption with a body that hides its nerves in the edges and a nose that soaks energy without reacting. The pilot now forces the one geometry the Raptor doesn't want: vertical. What happens when a naval gyro gun has to track a target climbing almost straight up from 200 meters off the bow? The answer starts the moment the pilot kicks the Beaver out of ground effect and into a steep climb. The silhouette changes in an instant. Instead of a thin, low smear against whitecaps, the drone turns into a narrow, rising line cutting across the sky over the bow. The gun mount has to swing up fast and stay precise while the boat is still committed to speed. That's a track the crew doesn't rehearse often, and the rates it demands push the system near its limits. The Raptor adds throttle to keep the drone in front, but speed works against the stabilizer. High knots stretch the turn radius, so the helm holds a wide arc. Roll couples into yaw. The deck heaves, and the sight has to correct in 3 axes at once. The gunner's reticle lags a fraction behind the climb. Each correction feeds the next, and any slight overshoot compounds. Elevation changes faster than the mount wants, and azimuth won't settle because the hull keeps slewing underfoot. Gyro stabilization can flatten out pitch and roll from sea state, but it isn't magic. Rapid elevation shifts while the hull yaws during a hard turn create a timing gap between where the gun points and where it needs to be. That gap shows up as overshoot, then a pullback, then another overshoot. Accuracy drops even if the sight looks calm for a second, because by the time the system settles, the drone has moved into a new angle and rate. Line of sight breaks make it worse. Every mount has hard limits baked in, mechanical stops, software rate caps, and blind arcs near the bow and mast. When the target's climb rate and angle exceed those limits, the tracker can't keep a clean solution. The Beaver's near-vertical burst forces the gun close to its upper elevation range, exactly where small changes in angle create bigger aiming errors. As the drone passes through that piece of sky, the system hits a short dead zone, loses firm lock, and must reacquire. Here's the aiming paradox the crew runs into at close range. The drone comes from short distance and climbs through the area right above the bow where the gun's geometry is worst. Too close for comfortable lead, too high for the mount's sweet spot, and moving fast enough to exceed rate limits. For a heartbeat, the Beaver sits just beyond optimal elevation. The gun hesitates on the stop, then dips to chase. And that delay gives the pilot a window. The pilot uses that window with a simple sequence. Climb hard, pause just long enough to freeze the sight picture at a higher vertical profile, then slip laterally across the bow. At that moment, the sea throws wake spray into the field of view. The superstructure cuts the corner of the reticle. Clutter and occlusion force the gunner out of predictive tracking and into reactive aim. Each burst starts a fraction late and ends a fraction behind because the system is now chasing, not leading. The boat tries to cut across for a clean line. The stabilizer hunts again as the hull banks. The gunner rides the controls, but the solution never stabilizes. The mistake is baked into the maneuver. By committing to a hard, high-speed turn while the target goes vertical, the crew drags their CIWS-style engagement out of its comfort envelope. The Beaver breaks lock, slides past the kill zone, and drops back to cruise. With the naval ambush beaten, the drone turns inland, hauling low toward air defenses and the aircraft they're meant to guard. Low-cost design and smart geometry beat raw firepower. The Beaver lived because the patrol boat fought the wrong battle at the wrong angles, forcing its own gun into lag, dead zones, and short-range occlusion. That isn't luck, it's method. Distributed systems, inert nose mass under pass-through hits, and a climb that pushed the mount off its rails. If you want more breakdowns of how small drones outthink big platforms, subscribe and tell us which system matchups you want dissected next. Next time, we'll show what a helicopter's radar sees when a swarm splits and one drone dives for a parked bomber.